Today's lesson is about exponential decay functions. It's section 8.2 in our book. Our learning goal is to graph exponential decay function and to use them to model real-life situations. So the first thing we need to do is to be able to recognize the difference between a growth and a decay function. So I've got here on the screen here the definition from section 8.1 of what an exponential growth function is. It's y equals a times b to the x, and the conditions are that a be greater than 0 and that b also be greater than 1. Okay, so that's going to make an exponential growth function. Now let me say real quickly that if a is not greater than 0, this number out in front, it's still an exponential function, but it's not a growth function. Okay, and a new definition today is for exponential decay is where y equals a times b to the x, and the conditions are different. Okay, well, back to this. Exponential decay is a function y equals a times b to the x, where the a is still positive, and again, if a is negative, we just don't have a growth or decay. It's an exponential, but it's neither growth or decay. A has to be greater than 0 to be considered growth or decay. And then the parameters for b are that it be greater than 0 but less than 1. Okay, so there's the big difference between growth and decay, is the value of b. Now I want you to think of what kind of numbers does b being greater than 0 and less than 1 describe. Alright, I'll stop for a second. Okay, well, we probably discussed that those are the numbers, those are the proper fractions, where the numerator is less than the denominator, or the decimals, positive decimals, 0.1, 0.2, 0.3, and all that up to 0.999, and as many nines you want to imagine. But anything, any value in that group, if b is that value, then what the function is going to be is an exponential decay function. Okay? All right, example number 1. We want to state whether the functions are, let's see if I can grab this out of the way, are an exponential, growth or decay. So are they exponential, growth, or decay? So we need to be able to tell the difference between these. Okay. So in number 1, then what we want to do is we want to look at the b number. Okay. Please note that this number, this a number, has nothing to do whether it's decided that this is growth or decay. It's just the a number. And since 2/3 is between 0 and 1, then a is, we would call a decay. Okay, so I'll write that a little neater here. This is definitely decay. All right, and as you look at b, again, the 8 doesn't matter, and don't be fooled because you see a fraction in here. It has to be a proper fraction, and since 3/2 is an improper fraction, or this is greater than 1, this would be considered growth. And this is going to be typical of questions that you're going to see on a test, is we'll ask you to distinguish whether something is growth or decay. And now c is sort of a curveball. When you look in here, you see the number 3, and 3 is definitely not between 0 and 1, but look at the sign of the exponent. Okay, so here's what we're going to do with c. We're going to rewrite c as y equals 7, 3 to the negative 1 times x. Okay, we can take that negative x and write it as negative 1 times x. Then if we slip in some parentheses right here, you have 3 to the negative 1 raised to the x. It's the same as that. Well, that simplifies into 1/3 raised to the x. And now what kind of value does that have? Yes, that does fit between 0 and 1, and this is definitely a decay function. Okay, so be careful of that negative exponent and the implications on the base. All right, I want to get you to try a couple of these. Tell me whether or not these are decay or growth. All right, back to you here. Number 1 is like that last one we had, so we're going to separate that negative on the negative x and separate that as negative 1 times x, and so you have 1/3 times 2 to the negative 1. You have 1/3 times 1/2, which is 2 to the negative 1 is 1/2, raised to the x, and this is clearly going to be a decay function. This one, 5/8 is no negative up here. 4 doesn't matter. It's all based on the 5/8, and that's definitely between 0 and 1. This is a decay. And we have another negative here, so really this one is going to turn out to be growth, and let me show you. Okay, so what's 1/2 to the negative 1 and then raised to the x? Power raised to a power, we would multiply these and we would get negative x. And if you remember our property that we have, a over b to the negative n is equal to b over a to the positive n, then we can use that on this and write this as 2 over 1, which is going to be 2 to the positive 1 then raised to the x, and this one turns out to be growth. So be careful those that have that negative exponent. If you have a negative exponent with a proper fraction, it's going to turn out to be growth because you're going to invert it or write the reciprocal of it, and that's going to put it outside that range from 0 to 1. Okay, how to graph exponential decay functions. Example number 1. We want to graph y equals 1/2 to the x power. Okay, so definitely between 0 and 1. And I've got the steps on how to do that over here, and I've worked this first one out for us. But step 1 in graphing exponential decay or growth is going to be to take the exponent, here the exponent is just simply x, and set it equal to 0 and solve that. Well, when I set x equal to 0, x is by itself, so it's considered solved. So then the second step is to make an XY tree with this value in the middle. So here's my XY tree here, and I put my 0 in the middle. Okay, now you remember that's because we believe that's going to be somewhere in the middle of the curve. Okay, and then what we're going to do, 3, is we're going to plug in values above and below it and get y values. So here above 0 is 1, 1 above that is 2, and 3 below 0, -1, -2, -3. And we're going to plug these values in. So when we plug in plug in 3 for x, okay, so we get 1/2 to the 3rd power. It's going to give us the value 1/8. So 3 and 1/8. That ordered pair is going to be on our graph. It's one of the points on the curve. When we put 2 in, 1/2 raised to the 2nd power is 1/4. There's our value. We put 1 in for x. 1/2 raised to the 1st power. Anything to the 1st power is itself. We put 0 in for x. Anything to the 0 power, regardless whether it's positive, negative, big or small, anything to the 0 is equal to +1. And then if we put -1 in for x, well then we're going to invert that and we get 2. If we put -2 in, it comes out to be 2 squared or 4. When we put -3 in, it turns out to be 2 cubed or 8. Okay? Step 4 is to graph these points and make a smooth curve through them. We do that in the next screen. Okay, or maybe it's the next screen. There it is. Okay, had an extra screen in there. All right, let's go ahead and graph these. So we have 3, and then the point 1/8, which is maybe just sitting right on top of the line there. Can't be very high. Go out to 3, up to 1/8. Okay. 2, and we're at 1/4, so it's just a little bit higher, but still pretty close to the x-axis. 1, we're at 1/2, so put that point right there. 0, we're at 1. -1, we're at 2. -2, we're at 4. And -3, we're at 8. Well, now that's quite a few points here, and as you remember from the last section, we don't normally use that many points, but just on this first one I wanted us to have quite a few so that we can see the nature of this curve here. And I'm going to try and freehand a curve. Freehand a curve through here. This is a challenge for me here. And we know that it's going to be asymptotic to the x-axis, and it's going to look like it's laying right on top of that line, but there's always going to be a little bit of distance between those two. Okay, so that's what this graph turns out to be. Let me clean that up a little bit right here. Got a little wild with my line. All right, so as you remember, exponential growths went like this, and exponential k is going to start on the left-hand side of our what we call the middle point, or the middle of the curve. That's where it's rising really fast, and on the right side it's falling very slowly. So rising fast over here, falling slowly over here. Our goal is to get maybe a point in the middle of the curve, at least one point on the rising fast side, and at least 1 or 2 points on the falling slowly as we look over here. So that's going to be our graph. That's what they look like. Okay. Example 2, graphing in the form y equals a times b to the x. Okay, so we'll take a couple examples here. Let's take a look at this first one. To graph it, we're going to take this and set it equal to 0, and I'm going to always place that in the middle of my chart here. And anything to the 0 power is 1, so we get the point 0, 3. Okay, go ahead and put that on our graph here, and so we can decide if we've got enough points or not. We just want to be able to sketch the curve out. Okay, well let's go one bigger than that. Okay, so we put in 1, so we have 3 times 1/4, or that's going to give us 3/4. Okay, so 1/4 to the first power is 1/4, and then that times 3. So at 1, we're at 3/4, so that's closer to the top here. All right, well, that looks like it's already going up pretty quick right there, so I'm going to go in the other direction. I'm going to go with, let's see, let me go to -1 here. Go ahead and do at least 1 on this side. If we put in -1, then we're going to have +4, and we're going to be up here at 12. So at 1, if this is 10, 11, it's off the graph, isn't it? So I'll kind of put it up here, but we may not use that point in graphing this. Okay, let's go one more in this direction, 2. And if we put 2 in for x, 1/4 to the second power is 1/16, and that times 3 is 3/16, and we're getting really, really small there. So at -1, I realize I put that in the wrong place now, didn't I? Okay, let's go back to that one, and when we put in 2, we get 3/16. Okay, I've got this wrong. Let me correct that. All right, erase this. And -1 was the 12. So -1 was up here at 12, and 2, it's at 3/16, which is going to be very, very low here. So we have enough points here to go ahead and graph this. So this is going to come in very steep and start curving through these points, and then we know it gets asymptotic to the x-axis. Very hard to draw that. I'll go ahead and put my arrow there and my arrow up here, and this is the graph of y equals 3 times 1/4 to the x. All right, let's try one here. Now this time a has got a negative number in it. Let's look at the effects of that. Okay, so we're going to set our exponent equal to 0, and that's going to be our starting point. It's already solved, and so let's go ahead and put in 0. 0, 2/3 to the 0 is 1, so we get 0, -5. Okay, so 0 and -5 is on our curve. All right, let's go to +1. We go to +1, and we get 2/3 to the first is 2/3. 2/3 times -5 is -10/3 here. Okay, and that's going to be -3 1/3. So at 1, we're -3 1/3 right here. Let's go to 2. And when we square 2/3, we get 4/9, and then we times it by -5, and we get -20/9. Okay, so that's a little over 2, because 18/9 would be 2, so a little over 2, maybe right about in here. Okay, so it looks like that line is going to be curving this way. I probably need to do a few more points in this direction. So I'm going to drop down here and put 3 in. Okay, and then 3, we're going to have 8 over 27, and 8 times 5 is negative 40 over 27. Okay, so let's say that's going to be, well, if that was a 30, it would be 1 1/3. It's going to be a little over 1, somewhere about in here. Okay, and then I think we're going to have enough there to draw our curve. So this line's going to come in something like this. Not a very smooth curve at all here. And go asymptotic that way. Let me erase some of that there. That's really sloppy. Going off in that direction. Okay. All right. Get you to try a couple of these. Go ahead and do these. All right. Go ahead and check your answers against these pictures here. Was able to do this one in 4 points. Felt like I got a pretty good picture. I'd made the turn. I was very close to the asymptote, the asymptote here. Remember that really quick about asymptotes is that our general equation, and I think I'll get it in the next screen, but I'll go ahead and say it now, a b to the x minus h and then plus k. We have an asymptote at y is equal to k. Well, on all of these problems we've done, there was like a plus 0 on the end, so our asymptote has been y equals 0. That's the x-axis, and it's already drawn in. So we haven't addressed that because our asymptote has already been drawn in. When it's not the x-axis, then we take a step to do that. Okay? All right, assuming there's no more questions here, we'll move on to the next screen. And our next example, example 3, graphing in the form, and let me move this out of the way again, y equals a times b to the x minus h and then plus k. Okay, let me kind of readjust this here. Get this where we can see everything again. I don't know what happened there. Anyway, there we go. All right, so for this is the first time that we've seen some numbers here and here, and this is our h number and this is our k number. And so if we're going to graph this, then the first thing we want to do, one of the first things, is go ahead and address what the horizontal asymptote. Now, horizontal asymptote, that wouldn't even fit on the screen, so I've abbreviated HA down here, and it's going to be the equation of a horizontal line, and it's going to be y equals 1 for this problem. And we go ahead with dotted lines and we go ahead and dot it in. Now this is the line that the graph is going to approach but never actually touch. Okay, so I'll dot in my horizontal asymptote. Again, these other problems, it's been the x-axis, so can't see a dotted line on top of a solid line. We haven't drawn it in. Okay, and the other thing is, the second part is that to find our starting point, or get that point that's in the middle of the turn or the curve, we want to take our exponent that we have, x plus 2, and set it equals 0 and solve that. So when we subtract 2 from both sides, we get x is equal to negative 2. And then that's going to be our guess that we put right here in the middle of our numbers, and then we'll go up and down as needed to get a complete graph. All right, so when we put in negative 2, of course that's going to change that to 0. Anything to the 0 power is 1, and then 1 times negative 3 is negative 3. Negative 3 plus 1, we get negative 2. So the point negative 2 is what we're going to think is about halfway through this curve. All right, and then we'll move, we'll get one bigger, put in negative 1. So negative 1 plus 2 is positive 1. A half to the positive 1 is a half. Negative 3 times a half is negative 3 halves. So here we have negative 3 halves. plus 1, but I'm going to write 1 in the form of 2 over 2. We know that if we've got fractions and we're adding, we have to have a common denominator. So I have to change 1 into a fraction that has a denominator that matches this one, and that's going to be 2 over 2. So negative 3 halves and positive 2 halves is negative 1 half. So negative 1, negative 1 half. So go to negative 1 and negative a half is where that's going. Okay. All right. So looks like to me this thing's going to be running in here somewhere. Let's try 0. Go one more bigger. 0, we're at positive 2. 1 half to the positive 2 is 1/4. We have negative 3/4 when we multiply by that. And then here we're going to add 1 in the form of something over 4. What is it equal to over 4? It's 4 over 4. And so we get positive 1/4 when we're at 0. So 0, we're at positive 1/4. Okay, still not quite as close to that asymptote as I'd like, so I'm going to go ahead and do a positive 1 down here. I know it's out of order, but I've got room. So we put this to the positive 1, we have 1 half to the third power. Well, that's going to be 1 half times 1 half is 1/4 times 1 half is 1/8 times negative 3. We get negative 3/8 and positive, and this time 1's going to be 8/8. So we get 5/8 here. So at 1, we're at 5/8. Now I'm feeling like I've made the turn here, and I can see where that's headed that way. And I think I can do this draw this with just these number of points here. If I can draw it, not get wild with this. Okay, asymptotic there. Heading off here. Now, this is the first time in this lesson that we've been asked to state the domain and the range and draw in the horizontal asymptote. We did draw in the horizontal asymptote. Now, let's talk about the domain and the range. So this is review, but the domain, we're always thinking of the x values or the x-axis. So if you look at this picture here, imagine how much of the x-axis this picture will eventually include. Well, it looks like this is headed just as straight to positive infinity as this graph can, although it's not going to actually touch positive infinity, or this line 1 rather. It'll keep going and getting closer and closer. So we're headed to positive infinity in this direction. And now a little bit about the way this thing is curving around. Okay, so what we've said in the last section, just like exponential growth, this thing, although it turns pretty quickly, it never goes straight down, or it never gets perpendicular to the x-axis like the y-axis is. So if it never gets perpendicular, it never stops moving to the right, and if it never stops moving to the right, it will continue to negative infinity. And so, as you can see, we're going to go forever in both directions, and so the domain of this function is simply all real numbers, and our way of abbreviating all real numbers is a script R. Okay, that's really not very neat there, but the capital script R represents all real numbers. Okay, the range has got to do with the y-axis, or how much of the y-axis will this picture eventually include. Can you ever imagine it getting up here to positive 2? I don't think you realize, since it's not going to cross this line, it'll never get this far, and since it doesn't cross this line, then it will be, and this thing's going on forever in this direction, we're going to include everything from negative 1 down. Now the way we can write that is we can say y is less than 1. I don't know if I said negative 1, it's 1 here. So our graph is going to be from here down, and the way you write that as an inequality is the y values are going to be less than positive 1. Okay? All right, go ahead and give one a try. All right, well, let's give this one a look here. Had some sticky looking fractions here. Decimals rounded to one place would have been just as good on this. I chose to do the fractions though. Okay, so it has a range of all real numbers, a domain of all real numbers, and a range of y is going to be always less than 3. Well, let's see here. Okay, slight correction on that. I did not draw in my horizontal asymptote, and I had this thing dropping down to the x-axis, and of course that's not true. So correction, the horizontal asymptote is 3, And our range is still y is greater than 3. So it's always going to be above that line. Okay? All right, let's talk about exponential decay functions and the decay factor. Okay? When a real-life quantity decreases by a fixed percent each year, the amount of the quantity y after t years can be modeled by the equation, and y equals a 1 minus r in parentheses raised to the x power, where a is the initial amount, r is the percent decrease expressed as a decimal, okay, and then the quantity r minus 1 is called the decay factor. All right, so that explains that formula for us. Let's go to our first example here. All right, example 4, using exponential decay models. Okay, here you're going to buy a new car for $24,000, and I think you can still get them for that much. The value y of the car decreases by 16% each year. Okay, step 1, we want to write, or for the first part of this, we want to write an exponential decay model for the value of the car and use it to estimate the value after 2 years. The second part is we want to graph that model, and the third one, use the graph to estimate when the car will have a value of $12,000. Okay, all right, so let's remember it's a $24,000 car and 16% decrease. So we're going to go ahead and put in our values. Okay, so y equals the initial amount. Our value of this car is $24,000, and it's going to be 1 minus, and that 16% change to a decimal is 0.16, and then raised to the t power. Well, we got to work on this a little bit. Y is equal to 24,000 times 0.84 raised to the t power. Okay. All right. So we want to definitely start with 0 here, and actually I don't want to put 0 in the middle because I can see that everything's going to be first quadrant here. So my choice of 0 needs to go on the bottom, and then I'll get to bigger numbers. Okay. Now let's go back to the problem and see. By the time the value of this thing is 1/2 or 12,000, that may be several years down the road. We may not want to do all these years. So let's put in 0, and when we put in 0, of course, we're going to get a value of 24,000. So our starting point is right here on this graph. We expect it to kind of slope down because it's exponential decay. And let's just go every other year. I'm going to go with 3. Let's see what 3 is. Okay, so if we put 3 in, then what we have is y is equal to 24,000 0.84 raised to the third power. Okay, well, when we put that into the calculator, we come up with 14,022. 1,422. Okay, I see where my mistake was. I left a 0 off here, and so when we put that 0 back on for the 3, we're going to get 14,224. Okay, well, our question was about 12,000, so I went from 0 to 3, and I took a pretty big jump. I'm going to come back in here and put the 2 in and the 1 in, and when we put in 2, okay, so that's going to be y is equal to 24,000 times 0.84 raised to the second power. And we're going to get 16,934. And when we put 1 in, we get y is equal to 24,000 times 0.84 to the first power, which is just 0.84. And we put 1 in, we're going to get 20,160. Okay, let's go ahead and graph these points. So we've got 0 and 24,000. Let's put in 1, and we're up to 20,160. So that's 21, and then 60, 160 be about in here. All right, at 2, we're at 16,934. So 15, 16,000, 934. So almost 17,000 right in here. Go back and revisit this one. This is going to be 20,060. So that's going to be more like right down in here. That looks like it's misplaced there. Let's go ahead and get that out of the way. All right, that looks better. And then for 3, we're at 14,224. So there's 15. Here's 14. 224 is just a little bit up from that. Right there. And then at the 4th year, we're at 11,948, or almost $12,000. Okay, it's right in there. So that should be enough for us to sort of connect these dots with a curved line. Not a very good line here, I see. Okay, so we're going to assume that thing's going to just keep on dropping, and it's going to start to turn and go maybe about like that. Of course, that would keep going up this way. And so what we want to do now is find out when. So go to 12,000 and come over, and we hit 12,000 right about here. So maybe right before that. So the question is maybe what year. So what year are we in? It's the year that between 3 and 4. So approximately or about 4 years. Okay. It'd take about 4 years for the value to drop in half. Alrighty. And let me get you to try this one. A new car costs $23,000. The value decreases by 15% each year. Same problem as last. Write an exponential decay model. Graph that model. Use it to predict when the value will be half the original. Okay. Give you some time to do this one. Okay, go ahead and check your graph against this one here. We still haven't answered the question, though, is at what year or how many years will it take for it to lose half of its value? Well, half of 2,300 is 1150, so there's 10,000, 11,000 halfway, and that appears to hit right about in there. So we'll look down here. And where is that on our chart? And it's going to be approximately maybe 4 years, or maybe a little bit more, slightly more possibly. We'll say 4 years. Okay? All right, well, I believe that's going to end the lesson. It does. I appreciate you watching, and have a good evening.